Yeah, okay, sorry. Okay, yeah, thanks a lot for having me here, for giving me the first time to be at IIS. It's my first time, I've never been here before. Consider it an honor that I can stand here and speak here. So I'm going to talk about uplift and flattening within the context of KKLT. This will touch some of the things that Renata and Andre already talked about. I hope we don't disagree on very many things in the end. And well, let me first say what this talk is, in a sense, as a boundary conditions, what it is about and what it is not about. So what I will discuss is a sketch of a 10D argument, and this will not make any statements about the whole KKLT mechanism as a whole collection of models, as a paradigm, if you want. It will not make any statements about the whole de Sitter landscape in string theory. There are many more de Sitter constructions. There's KKLT is a whole paradigm. There is other constructions besides KKLT, and I will not be able to say anything about that. There are variants of KKLT that even if the discussion I'm showing has merit to it, will still work. For instance, the Karosh-Linde variant of KKLT is fine, as you will see. And the potential problem, the possible problem that I'm going to discuss so far concerns only the very simplest example of the KKLT mechanism, which is essentially living on a Calabi-Yau manifold with a single volume modulus and a single source of Gaugino condensation. So a single stack of D7 branes. Only then, only for that case, I will make my discussion. And I can already, the discussion is not closed. I will not tell you something that I will consider as, it's the end of the argument. I will give you some arguments that are in favor of a certain conclusion, but I will also tell you where you have to go on to analyze further before you can come to a conclusion whether these arguments are conclusive or not. So let me review for that purpose although you probably all know that, I mean, like the kind of arguments that go into the original KKLT paradigm construction mechanism. So the zeroth order step is basically warped flux compactification of type 2 string theory on conformal Calabi-Yau manifolds. That goes back to these authors. So basically what you have is, in order to get warped solutions, you need, with such a background metric, you need ISD fluxes. You have flat Minkowski space in 4 dimensions. You have to introduce certain O-planes, and then stack either 3 branes or 7 branes on top of the corresponding fluxes, and then you get a solution that fixes the complex suction moduli generically. It fixes the axiodilaton, but it leaves all the volume moduli of the Calabi-Yau unfixed. So you get a no-scale solution. And that's what you get when basically all local sources, everything is BPS. Okay, and that solves the 10D Einstein equations and Bianchi identities for the P-form fluxes. Okay, then in the next step, the proposal is that you add a non-perturbative quantum correction to the superpotential that together with this scalar potential, the effective 4-dimensional supergravity for that single, in the simplest case, single volume modulus of the Calabi-Yau, which is this T field, chiral field. Yeah. You get that potential, which is a supersymmetric anti-de Sitter minimum. And then the proposal is to add an anti-D3 brane at the end of the warped region that has been generated by the fluxes basically in a deformed conifold of the balance throat. The anti-D3 brane settles at the bottom. It creates a metastable SUSY breaking state. And then by arranging the warp factor the size of the superpotential from the fluxes W0 the right way, you lift with almost no shift of the volume modulus. You can lift to 0 vacuum energy, and above you get a barrier. You have a de Sitter minimum. Okay, so that is, so to speak, the original construction. And as already was reviewed, there's a lot of work has been going on. There was realized that this SUSY breaking can be phrased in terms of nonlinear of the non-linearly realized supersymmetry of the entity free band in terms of a nilpotent superfield. So then you basically can extend your Kähler superpotential by these two terms, and the F term for the S field then reproduces the anti-D three band term. Okay. Now, what I will now look at is the particular type 2B version of what is called the Malvasina-Nunez theorem that was written down by Giddings, Katzor, Brzezinski first, and then basically just reformulated in a way by Heidenreich, McAllister, and Toroba in 2010. So basically this is that you combine the trace reversed 10D Einstein equations with the Bianchi identities for the phi form flux, and then you get a condition like this, which has to be basically valid on the solutions that you get. And when you integrate that over the Calabi-Yau manifold, then you get therefore a condition that determines the 4D curvature, scalar curvature, in terms of various local, objects, localized objects, and the flux densities. The O planes, the D branes, they all go in here. So this kind of thing would then determine in the end whether the sign of the 4D curvature is positive or negative. If you want to find a zither, of course, you should in the end find this positive. So now the point is that it was already discussed in Malvasina-Nunez. You get certain no-go theorems for de Sitter from linearly realized supersymmetry. Now, if this condensation effect, this non-perturbative quantum effect in KKLT, comes from gauge-Gino condensation, if that gauge-Gino condensation effect on a stack of 7 branes has intrinsically 4-dimensional aspects that cannot be captured by a 10D description, then I could stop, because that already is a loophole to the Malvasina-Nunez theorem, and then I'm already done. I can't go on with that, applying that theorem, and I would be done. Then already, at that point, I could stop. So. Yes, that's true, but they are then paired with 7 branes in a way that they actually just satisfy the equation of the motion, that you get a no-scale solution back out. Yeah. yeah, that's true. Yeah, but for the last step, so to speak, I mean, like, if this gauge-Gino condensation is a manifestly 4D effect or has 4D aspects that I can't lift into 10D, then I could stop here already. Now, the point is that what I will follow is work by Heidenreich, McAllister, Toroba, and Dimarsky and Mantucci from 2010 and 11, that who basically gave a description for the effects that gauge-Gino condensation on a stack of 7 branes, so the formation of the lambda-lambda bilinear, has in terms of a back reaction on the 3-form fluxes. The 7 brane sources extra 3-form fluxes. There's a lengthy calculation you can do, and then the presence of the condensate when this is non-zero has such a coupling to the 3-form flux, and that sources 3-form flux is the source and the flux equations of motion. You can compute these 3-form fluxes. It has been done. And now the proposal that was made here is that if you want at least to leading order in the alpha prime expansion in 1/volume expansion of cycle volumes of the Calabi-Yau volume, that this should represent or describe the gauge-Gino condensate on a stack of 7 branes in the 10-dimensional setting. That will capture everything that you normally would describe 4D. This is a conjecture. It's something that is it's not proven. So if you run with that, you can compute from these fluxes that these coupling sources what these fluxes contribute to this delta quantity, this so to speak, right-hand side of the Malvasina-Nunez theorem. And then you see that there is a positive contribution and there is a negative contribution. And if you apply that, just you want to reproduce the supersymmetric anti-de Sitter vacuum that you get in the 4D supergravity of the single modulus KKLT example, where you find a SUSY ADS vacuum, then you see that you have to choose, because they scale for a single condensate. There's NS1 here. You get the same 2 terms here. You see that then you must find C bigger than D, so that the delta is positive, because the positive delta, if I go back, tells you that then the sign of R4 is negative, and that's ADS, 4-dimensional ADS, and the sign of 4-dimensional ADS, which you should find at the SUSY ADS point.
So I was also going through this paper by Martucci and
this I agree. This is this is something where more work has to be done. I agree. I completely agree. So at this time, I'm just saying, this. If you want to represent the supersymmetric ADS vacuum, then this gives you this kind of, that the C must be bigger than D. There's a number here basically that in the end will have to be calculated, but this inequality has to be satisfied. Then you reproduce that, you get a supersymmetric anti-de Sitter vacuum. And now there's the conjecture basically made, yes, if the anti-D3 brane as a local object locally basically behaves to leading order the same as the D3 brane, and the delta log, the contribution to the delta from the anti-D3 brane, that has been worked out already in GKP, and then later on again here it was restated, it's positive, not negative, then it looks like you on this, on the right-hand side of this rewritten Maldacena-Nunez kind of theorem, you only get positive deltas, which leave the sign of R4 negative. That is, if you want, our reason why we think that in that simple example, in the leading effects of in expansion of 1 over volume, we do not seem to find that this flips sign to positive. And at least in that's at least, like what this contribution for this delta is, yes. Yes. Yeah, but this is this is T mu mu minus TMMP, so to speak, right? I mean this. Yeah. Well, it is a positive tension object, but effectively, what happens is when you insert its contribution into the right-hand side of the trace reversed Einstein equations, subtracted by the Bianchi identities, then you get this delta quantity, and that is positive.
So where's the positivity is coming from?
The negativity in the contribution to R, yeah.
From D3, from the Martucci computation for D3, not for anti-D3.
Yeah, but this formula is already in the Giddings-Karlsruhe-Polchinski paper for anti-D3s. They make the same statement. That's not something that we invented or something like that. To delta log is positive, and then therefore, if you bring all the deltas on the right-hand side of R4 equal, then it contributes negatively to R4.
So then there was no need for using Martucci.
No.
This really demands an explanation of how you're getting something negative out of a positive tension object. I haven't understood that yet. And I know you have in mind some kind of catastrophic back reaction. You have in mind that there's something that reacts that drives it negative.
We haven't explained that yet. Yes, I agree. I agree.
In order to keep right, okay. So
Yeah.
in order to in B and C language, I forget who's B and who's C. To have a big back reaction effect from a small perturbation would require an underlying instability in the model, and yet when people tried to assess that, they found no relevant operators that could be source and that sort of stuff. So I think one should just this is looks very complicated, but there's a very simple question at heart here, which is there's a positive tension object that's redshifted down. That is the way they modeled it. What's wrong with that?
No, exactly. The question is, if there's truth to this observation, you should basically find that the positive tension object, which is the anti-brane, sitting at the bottom of the warp throat, it pushes on the volume modulus that basically changes the value of the Gaugino condensate. That is a back reaction effect, and that should be there should be a mode communicating this back into the IR, effectively shifting the warp factor there. If we find such a mode, then we would understand really what's happening. We don't have that understanding yet, and this has to be cleared up. And it is not, the mode is not among the classification of the massive KK modes that is, for instance, in all the papers by Liam and Daniel, and they did in the 2010 this holographic dictionary basically. It's not part of that massive mode. It would have to be something that is a very light mode in that throat. There's, for instance, some work by Andrew Frey that claim that there are light modes. We don't know that yet. I mean, we have to look for this. And it may be that the mode is absent. And if the mode is absent, then I would conclude that something with this 10D answers to describe gauge genome condensation in 10D is incomplete. Something's missing there.
This 10D analysis, it's a heroic effort, but it has some steps where you kind of make an assumption or hypothesis about how it's going to go, right?
Yeah.
So that is, I mean, to me,
The,
that's has to be countered with just the basic physics that it's a
I agree. I agree.
Again, there's no
yeah.
unstable mode in the KTLT roads.
Yeah. No, and we would not expect to find an instability, but there could be a mode that creates a shift of the warp factor building up in the IR, which is finite, but and maybe that's a mode is absent. We don't know that yet. But that analysis has to be done. We have started that. We are not there.
But again, this hierarchy between B and C doesn't make much sense unless there's existing instability.
Yeah, and yeah, I would say not an instability, a mode that is so light that it can communicate a large back reaction effect back down the throat to the anti-brain, to the warp factor there. I'm not sure whether I would phrase it as an instability. I don't think that the vacuum will just go into runaway because of that, also, if you mean that with an instability.
I'm just saying you're putting a priori small perturbation in there and getting a large coupling between something that's in a highly reticent region and something that is not. Normally, if there's no other direction that is unstable, field lines spread out, the interaction is very weak. That's the basic physical picture.
Mm-hmm.
That's why we can't see directly black hole horizons. I wish we could, but we don't have a direct coupling there. So, I think that's the question that everybody has about your argument.
Mm-hmm. Mm-hmm.
So I'd appreciate.
No, the question is valid, and we haven't answered that yet.
Okay.
I completely agree.
What's the expectation that this delta log will not be positive anymore if you take it around the?
No, for instance, I mean, one way is that it could be missing something in this 10D flux description of the gauge genome condensate, so that this, for instance, turns negative. When you start to push on T and therefore try to to push.
So what's the expectation that this will change, or just that there are more contributions that
I guarantee you that GKP was not saying that the anti-3 brain contribution to the potential was negative. I guarantee you that's not what they were saying. I think it's going back to the history of the subject. It's very easy to get confused about these trace release reverse things and saying that some positive contribution is negative. I had funny debates with people about the flux terms, which are obviously positive, E squared plus V squared, but in some of these things, it comes in with some opposite sign that confuses people. This is a positive tension object. Think about it in the 4D effective theory. Its leading description is a positive tension object in a highly reticent region. That is a positive contribution to the potential energy. If it triggers some big reaction, there has to be, a reason for that. It's not a simple issue of a sign and.
And when you say positive contribution, means that then this delta log has to be negative.
I mean that it's a positive tension object. I'm just a simple person. It has positive tension. So think about the 4D effective potential. It contributes positively. Take an anti-3 brain in any compactification you want. Do you agree that contributes positively to the potential energy? So I made it anti and 3 brain because then Gauss's law satisfies. There's no issue.
The thing that I don't understand is, I understand, okay, you say positive tension has to contribute positively, but then I don't understand the meaning of this delta, because it's true, I mean, when you check the paper, like the delta is equal to like the 7 minus p, the dimension of the brain, times the tension. So if the dimension of the brain is more than 7, they say that this delta is positive, it means a negative contribution. And I always have the question, like, then what is going on? I mean, how you get with the anti-DC brain?
But is it really that I'm gonna flip it back to 10D because this KGN condensate, I understand right, it's really 4D effect, so it's not clear. You already down in the effective theory, so you cannot take that effect and apply the.
This is that was my way of that's what was my way of using it. It is definitely possible that this way of describing or trying to describe gauge localization in 10D is incomplete, missing something.
It's just similar to Casimir effect. When you kind of calculate Casimir effect, you cannot take it back, and you like you already kind of in Lorentz theory where you don't sit local inside your vector
Yeah.
dimension, so you cannot take it back and use it with the usual P mu in
And
high-dimensional theory.
it,
And I think this gauge
yeah.
kind of set is very
And
it's non-perturbative
yeah.
version of Casimir effect.
Disconnect.
So it's
Yeah.
very connected to Casimir.
Yeah, and if that happens here, if
It's very subtle to try and do that, and I mean,
So that maybe that resolve this confusion because this delta local that description from 10D
well,
point of view.
this is exactly why I was trying to separate the two things. I was trying to ask if separately you're saying the anti-brane, forgetting about whatever else is there, is somehow contributing negatively by itself.
That is true.
If you're saying that is, you know, that is in a way that has nothing to do with the gauging of condensate.
I think the analogy between D3 and anti-D3 is not working. That is, I mean, central part of
that is
10D
that's
issue.
that is definitely possible. And in my way of thinking, I would like to basically study these modes that mediate the coupling and either see if the mode is there or not. In the end, it may very well be that.
Reduction of this system, that's it. You know, localized sources, delta functions, positive tension on this anti-3 brane intervention region. You know the classical answer to that, and it's.
Yeah, I think the problem is that if you just take this delta, you don't distinguish between the D3 and anti-D3 because both have the same tension in that sense, and then you get the delta positive.
No,
But the difference
the
is when you have
computation
oriented
was
force.
due to dependence of the term A of phi times
But
e to the minus at, and this was an assumption that there is a back reaction on existing D3.
Yeah, exactly.
Therefore,
So
the
that's what I wanted to
superpotential
say.
had a very special term, and this is what Demarsky and Martucci computed on 100 pages.
But
But
sorry,
then
that's
you don't
important.
take
So
this
if you take the
formula
proof
directly
approximate,
into
so
anti-D3. It's just
D3
different
and
system.
anti-D3 is the same, but if you take into account that you also have oriented force and you have some calibration
It's
and so on,
different.
it becomes the same.
And there
And
is
I
no
don't know how this
computation.
change is clear. Yeah, but that's
It
the
has
point.
to
Not
be
you
a different
everything
computation.
at the same time.
Yeah.
I mean, they are different when you take into account that you already have an oriented force and you have some orientation, and then you can distinguish between the
But
two.
it was, they never added anti-D3 in 10D. And the reason I was doing it now, I noticed precisely this issue that Martucci and Demarsky only added D3, and therefore it's a different system.
From my point of view, I mean, like at the moment, there's clearly the possibility that when you do this, this analysis using the perturbation mode similar to as it was done in this, this warp D3 papers, basically, that you may find that this, the way how you describe the condensate in this 10D answer that is just incomplete. It misses something. And then.
Interesting result. I mean, the gauging of condensate by
Yeah, but I mean, the thing is that it may not be complete, right? I mean, like it may just not capture everything, and then there might be something that's really intrinsically 4D, for instance, that cannot be captured by this, like you say for the Casimir energy. And if that's the case, then of course this argument doesn't hold anymore. Okay. Now, the thing is that even if that argument were to hold, then you can see that at the moment you have two of these condensates coupling to the same volume modulus, this racetrack setup of Kader-Schlinde. There's a phase here, and then this kind of like sign that you had that seemed to give you negative R4, then actually, essentially by tuning, arrangement can be brought to be as close to zero as you want, as you see from the 4D supergravity point of view as well. And then, we would not then even if they were all true, then you would just need a very, very tiny amount of extra energy coming from adding the anti-D3, and then we would say that then you can get the zitter. This is what Andrea already had on the slides. In that case, there is no problem getting into the zitter once you have a racetrack. So some of the things we already discussed, I mean, we don't know whether we capture all of the leading effects of the Gediner condensation process with this, this kind of flux sourcing that has been described in the literature. We would like to know, in some way, if you even believe that this is capturing everything, you would like to see this from F terms on the 7 branes directly. If you move T away from the supersymmetric point, that you capture the same as you would know from the 4D kind of effective field theory description of gauging condensation. And then it's the CFD description in the throat. I mean, these kind of modes, the mode analysis that we may tell you maybe the mode is there that makes this consistent. Maybe the mode is not there, and then you know that something's missing. Okay, let me now move from that shortly to this the second step. That is basically if you assume that there is something to the 10D argument and that this sign is negative in this one simple model with a single Kähler modulus, in that particular model with a single gaugino condensate, can you modify the 4D supergravity description of the single modulus KKLT example in order to depict that you will lift but you will not cross into the zitter? And one proposal was basically that you add this piece in front of the nilpotent superfield in front of the exponential. This would produce such a kind of flattened lifting where when you lift for a while almost vertically, but then you start to shift the volume modulus instead of crossing into positive territory. That model, as Andre already showed you, has indeed the problem that there is a point where basically Fs can be sent to 0, and then this is inconsistent with a description of this whole nilpotent formalism of the Fokker-Vakulov description behind it. So before I now come to ideas how to fix that problem, now I will try to tell you one thing, how we think if you stay negative, what it really means in order to match to this kind of supergravity modeling. I mean, these proposals are not a dimensional reduction of the 10D thing. It's just they are meant to match this kind of flattening out of the uplift. Now the thing is that the statement that if the sign of the 4D curvature stays negative, it stays so within the leading 1/volume approximation. So that means eventually you will have perturbative corrections, which are at order alpha prime squared. They are down by powers of the volume, and you should basically choose this number C in that simple toy example of the supergravity modeling so big that you lift so close to 0 that any remaining lift from, say, the B coupling is comparable to the size of the unknown corrections. Because then what the B coupling does is basically, in a regime where you don't know whether the corrections bring you further up or down again, and you are, so to speak, you would then say that in the leading 1/volume expression matching to this 10D description that I was proposing, you then don't know whether you can control, use the B coupling in a controlled way within the size of these corrections to go to de Sitter or not. And that gives you a minimum size for C, which, in that simple example here, you basically, the C is proportional to this gamma is of order 6. And then you see that you already lift so close that you are sitting here. The T is shifted a lot. And if you then add the B coupling to actually formally go to de Sitter, the colored bands are the size of the typical, corrections at order whatever alpha prime that you might expect, or alpha prime squared. And they are then big enough that you cannot decide anymore whether the B coupling actually gets you into a de Sitter minimum or whether you basically are already losing the minimum. So then you would say that in that situation the B uplift, the B coupling is not in a controlled regime. And this is how we view the use of these effective supergravity models to be used. That you first lift to basically to the point where the 1/volume leading approximation reaches its limit of validity, and then you cannot use the B coupling in a controlled way to say, do you reach de Sitter or not? But this is under the assumption that you believe the 10D argument. It's just a match to the 10D argument. This kind of, that C shall be so big. Okay.
So essentially, you look at the 4D model,
Mm-hmm.
and 4D model in the range of its applicability gives you uplift to de Sitter. But if you choose huge value of C so that you go out of its limit of applicability, then you do not know. And that's essentially what we say. As long as you are in the limit of applicability, it gives you de Sitter. If you're out of the limit, then you are relying on 10D, then you do not use this 4D model.
Yeah, I would say the logic that we use is the following, that the majority of the lift should come from the C coupling. That is what the 10D argument, if you believe it, would tell you. Of course, if you don't believe the 10D argument, you don't have to do that. And I completely agree. At the moment, you don't buy the 10D argument. You can make C smaller, and then all what you have been saying is right. I mean, like that. At the 4D level, you're completely there. There's no disagreement. It's just that we are saying if you buy the 10D argument, then essentially 90% of the lift should come from C. And then you basically can show that then the remaining piece that could come from B is of the same size as of the unknown corrections, perturbative corrections to the potential. And then it would be, you can't know whether you get the zeta from that or not anymore. But only under this assumption that 10D is there. So this is, okay, sorry, I forgot something. So there was this problem that you have this the 0F term for S, in this original model. So we, like Andre already discussed, we proposed this change where you move this into the Kähler potential by a Kähler transformation. So our idea was having this function f0 and then the function g like this. In that case, there is no point where the f term for s or fs squared would vanish. But you found this as well. There's basically, you have a variant. This is where you call this c, and then and f is 0. So you found the same kind of that. This cures the thing. But again, the same discussion applies. If you buy the 10D argument, then you would have to make G1 so big that you get 90% of the lift. If you don't buy the 10D argument, you can go at any intermediate regime, and then of course the 4D model behaves. Then you find zeta points in the 4D model. So for me, sorry, that was backward. For me, the situation is that for the moment is that there is still a lot of work to be done to understand what this interaction between the Gauge-Jena condensate and the presence of an anti-D free brane is. In which sense the Gauge-Jena condensate is really described in 10D by these flux effects. Is it complete? Probably, maybe not. And then, before we do that, we cannot make a conclusive statement. Yeah. But for me, it serves as a motivation to look further, because this is the flux effects are clearly there. That there are these couplings on the 7 brane. They source these fluxes. To take them into account and see what they do in presence of the anti-brane is something that is worthwhile looking. And I cannot give you a final statement on what the final outcome will be at the moment. And I repeat, this is only everything we did was in this single modulus example for one Gauge-Jena condensate. About anything else, we can't say anything. Thank you.